Thank you very much. It's a pleasure to speak here, and thank you for the invitation. As promised in the abstract, it will be a bit strange talk, mostly about definitions, examples, and the language. And my goal is not to present you like a lot of concrete results, but maybe to summarize several mini courses, the one of Jeremy, Julia, and Susanna, and maybe to put it in from to consider from slightly different perspective, and maybe at some places generalize a bit. I'll speak about equivariant, birational geometry of surfaces, and of course I'll focus on surfaces which are geometrically rational and have a structure of Mori fiber space equivariantly. And first, let me explain what I mean by equivariant. So by equivariant, I mean two things. First, well, of course, we need an action of some group. And in the mini course of Julia, for example, this group was implicitly the Galois group of the field. Okay, so it was well, what is called now often an arithmetic situation. So I have two settings. First, arithmetic setting, where I work over in a field K, and my group G is the Galois group of the field, the absolute Galois group. Maybe, well, once again, since I will be using the Sarkisov program, I assume to be sure that the field is perfect, although now we have a generalization for arbitrary fields. And the second setting is geometric setting. When G is the automorphism group. For me, it will be finite, but maybe you can take algebraic. So G is an automorphism group. Finite, let's say finite. In this talk. And then, once again, coming back to Yulia's talk, she was speaking a lot about Sarkisov links centered at some closed points. So what is closed point in this case? It's just a Galois orbit, okay? A Galois orbit. So probably I will not explain anything. I will not explain terminology in arithmetic setting because we saw it a lot during previous 2 weeks. But for this setting, let me just maybe say that instead of vocabulary. Instead of K maps defined over K, we consider G equivariant maps. Okay. Instead of closed points as in Julia's talk of degree D, we consider G orbits of size D, G orbits of size D. What else? Well, instead of, I will consider Mori fiber spaces. So in that case, you assume that all your surfaces and curves are acted by this group G, and then the most important condition is the one on the Picard rank. So for example, so instead of Mori fiber spaces over K, I consider G Mori fiber spaces. Once again, I'll mostly focus on surfaces, so for me it will be for example, in dimension 2, this will be surfaces S equipped with a morphism to B, the G morphism, where B is either a point or a curve, okay, such that in the first case I have that, okay, maybe it's not good. So in the first case I have that the equivariant, G equivariant Picard rank of S is 1. And in the second case I have that it's 2. It's 2. And in the first case, I speak about Delpezzo surfaces, or more precisely, G Delpezzo surfaces, and in the second case, it will be G conic bundles. Here it will be G Delpezzo, and here it will be G conic bundle. So once again, we saw it a lot in courses of Yulia and Susanna. Everything is the same. I just put G everywhere. Consider G equivariant maps, G equivariant Picard ranks, etc., etc. Good. Now let me give you some examples. Examples of G Mori fiber spaces. So geometric. I start with geometric one. Let me go. Geometric G Delpezzo. Geometric. Yeah, and I will refer to these objects here as to G Mori fiber spaces, G Delpezzo surfaces, and G conic bundles. And I will not specify. I mean, and G can be either a Galois group or a automorphism group. Okay. So when I say geometric G Delpezzo, I mean that I work with automorphism group here. Okay. Where? Yeah, I'm in this geometric setting. Good. Then, well, an example is the following. I can take the what is called the Clebsch diagonal cubic. So I from 0 to 4. Clebsch diagonal cubic. The Delpezzo surface degree 3, right? And I need to give you some group G which acts on this cubic. There is an obvious choice, right? Which one? Like S5, which acts by permuting the coordinates. Okay, so S5, let me call S. So the group S5, in fact, this is the automorphism group of S, the whole automorphism group. So it acts on S, of course. And you can check that the GPK rank here is 1. So Clebsch diagonal cubic is an S5 Mori fiber space, S5 Delpezzo surface. Okay. Second example. So that was geometric. Let me give you arithmetic. Arithmetic Delpezzo surface. Arithmetic G Delpezzo surface. Well, I don't know whether it's a nice terminology, geometric arithmetic. Actually, I think it goes back to Manin. I still like to use it for this kind of problem. Arithmetic G del pezzo. First, example 2.1. Let me take the generalized Segre cubic. Once again, I take cubic surface. So it will be a 0x0 cube plus 1x1 cube. Something like this. Over rationals. So it will be over rationals. Then there is a beautiful theorem of Segre, which says that, so let me call it S. There is an explicit condition when this cubic S has pk rank 1 over Q. So rho of S, maybe for brevity I will denote rho of S, is 1 if and only if the following fraction, so it's a sigma 0, a sigma 1 over a sigma 2, a sigma 3 is not a cube, for any permutation sigma. For any sigma minus 4. Another example, the 2.2. This time it will be over reals. So this is a cubic surface, degree 3. Let me take S at del pezzo degree 2, given by the equation w squared equals f4x y z, defined over the reals, over the real numbers. So this is an equation in the weighted projective space with weights 2, 1, 1, 1. And the Galois involution here, which sends w to minus w, is the famous Geyser involution, which appeared several times already in this, even today, actually. Good. So this is a real del pezzo surface. Let's look at the curve defined by f4. So I take B, the curve in P2, defined by f4. This real curve, I can look at the real locus of B. So B of R is the bunch of ovals on P2, okay? A priori, it's not clear which combinations of these ovals are possible, okay? So there is a classical theory of real curves, real plane curves, and actually for degree 4 we know what are possible configurations here. But anyway, the theorem of Commissati says that so it's an old theorem, like the beginning of last century. It says that rho of S is 1 if and only if B of R if and only if B of R consists of 4 ovals in the following position. So B of R, so this is 4 pairwise non-nested ovals, okay? This is equivalent to the condition that, so we know that for quartics, plane quartics, we have 28 bitangents, okay, in this classical theorem. And this condition over there is equivalent to the condition that all 28 are real. All 28 are real. Anyway, all 28, so all 28 bitangents to B are real. Okay? A priori, they can come like in complex conjugate pairs. So my point is that it's an explicit, very nice geometric condition in both cases, which tells you something about the Picard rank. Now, so that was an example of a G-Mori fiber space. Then we have well, I will not introduce what a Sarkisov link is, because like we heard a lot about it. But just maybe to remind you that in arithmetic, so maybe it will be example 3, arithmetic Sarkisov links, arithmetic G Sarkisov links. So we saw a lot of them. In Julia's talk, we saw these Bertini involutions. Bertini involutions at points of degree 8. The one which appeared in the paper of Stefan and Susanna. Then we saw element transformations from Julia's construction of homomorphism, which were between Hirschsprung surfaces. Then we saw the links between Severy-Brauer surfaces. Which were 3 links or 6 links. So here S are non-trivial Severy-Brauer. And of course, we have many, many more examples, but I stop here. And finally, geometric Sarkisov link. Geometric Sarkisov link. I'll give you just something very, very trivial. So let me start with P1 cross P1. P1 cross P1, del Pezzo 8. Will be S. I don't need this. Acted by a group G, finally group G, such that the Picard is 1 here. Okay. This is possible, but I also want that G fixes a point. Then we have something classical which is called stereographic projection from the point. Formally, from like in the language of Sarkisov program, you do the following: you take this point, so you take this point, say P, okay. You blow it up. You get a del Pezzo of degree 7, but on this del Pezzo of degree 7, we have the following configuration of -1 curves. Have the exceptional divisor over P, EP. And I have 2 strict transforms of fibers which passed here through P, okay? So we can make, so these 2 curves are G invariant. We can, and they do not intersect each other, so we can construct them. And where we go actually to P2. So construction of, let's say, A and B. Not just contraction, but G contraction, I mean, equivariantly. G contraction of A and B, and we go to P2. So this is the instance of so-called linearization of a group. I'm not sure that I will have time to speak about it, but what I did here, I linearized the action of G. Good. I think that's it for examples of G-Mori fiber spaces in different settings. Now let me address the following very, very general question, which maybe doesn't make much sense, but still. Can we classify G-Mori fiber spaces? Well, of course, we need to specify up to what. So classification can be biregular or birational. Or birational. And that will be part 2 and part 3 of my talk. Was it part 1 actually? Yeah, part 2. Part 3. So what about biregular classification of G-Mori fiber spaces? Well, once again, I have two cases. I have arithmetic and geometric. I have Galois case and finite group action case. So arithmetic. Well, here you basically want to use the Galois homology, I guess. So we know what are automorphism groups over the closure of the Delpetta surface. For example, then you want to classify forms of, well, for example, Delpetta surface or conic bundles. So this is really the question of, I don't know. So want to classify, want to describe, classify. Delpetta surfaces. Conic bundles. Up to chi isomorphism, up to k isomorphism. But not only this, of course, we need a modifiable. We need also the condition Picard rank, right? So we also need to select those which have a Picard rank 1. So there's some extra work. Plus select those which have Picard rank 1 or 2. Well, I'm not aware of any general results in this direction. You can choose your favorite field and then try to solve this problem. For example, I already mentioned this work of Kamisatia. He basically classified real conic bundles and real Delpetta surfaces R. So he got this classification over R. You can go through this list and see which one has Picard rank 1 or 2 respectively. So classical work of Kamisatia. When K is R. So yeah, in this case we have the description, but I'm not sure that I don't know. Well, maybe you can, but for example, over Q, I think this is already quite difficult. And probably even for quadrics, to classify quadrics over Q up to isomorphism. It's something non-trivial, right? Anyway, what I want to say probably is that here I'll not give you more details because this is a bit different topic. What I can mention here is that life is a bit easier if you insist on rationality over the base field of your modifiable space. Namely, there is a theorem of Yasinsky which is the following. Let me take a geometrically rational surface, so S smooth, geometrically rational smooth surface such that S k bar rational. And assume that it's also minimal. S is minimal. Then S is rational over K is K rational if and only if the following two conditions are satisfied. So first, I need a K point. And second, I need that Ks squared bigger or equal than 5. So why I mentioned the theorem? Because at least, I mean, it's quite general, it's over any perfect field. So K is perfect here. K is perfect. But for example, it tells you that there are no K-rational arithmetic Delphi surfaces of degree 2 or 1. Okay? If I say that Picard rank is 1. Now, to the geometric classification. I mean, that was arithmetic. What about geometric? Here I need to classify first all possible automorphism groups, right? And then to select those for which I have equivariant Picard rank 1. What is the problem of classification of finite subgroups? Of finite groups. Finite groups acting on Delphi surfaces or conic bundles, plus conditional Picard rank, plus selecting those for which G current Picard rank is 1 or 2. And surprisingly, well, maybe not surprisingly, but it's still, well, we have like many missing cases. So just to mention what is known, well, on the other hand, many things are known, but when I work over C, like, or algebraic closed field of characteristic 0, then there are many classical works which accumulated maybe in the book of Dolgachev, classical algebraic geometry, and later in the paper of Dolgachev and Yasinsky about finite subgroups and Cremona groups. But anyway, here we have a complete classification. Complete classification. What about arbitrary fields? When K is perfect field, We have a classification of groups acting on Delpezzo 5 due to Aurore. I think she will speak about it on Friday, which is very recent. I mean. And then by Zaitsev. So both are 23 for Delpezzo of degree 5. Sorry? Yeah. I mean, they classified all forms. They described completely surfaces of degree 5 and finite automorphism group. Here, I mean, okay. Well, I agree that by geometric it can mean two things. So here, I don't assume that the field is closed. Okay. So G is a finite group in automorphisms of X. But yes, in practice, you of course go to algebraic closure, right, where everything is defined, and then you consider the action of G times the Galois group. Yes, you're right. So I'm a bit sloppy here. But I want to say that they completely classified like automorphism groups in aut X for X, a surface defined over K. Okay. Then what? Julia and Susanna, they did it for rational Delpezzo degree 6, I think, and connected groups. But okay, since I'm speaking about finite groups, maybe I will not write it here. Characteristic 0 case. So characteristic 0 case. We have the results, the classification of finite subgroups, but I think avoiding the description of forms of Delpezzo 3 and 4. So Smith, the student of Alex Duncan, in 2003, 2004, he did the classification for Delpezzo 3 and 4, of degree 3 and 4. And then we have a series of papers of Dolgachov and Martin, which solve the problem completely solve the problem for algebraic closed field of characteristic 0, positive characteristic, sorry. Complete classification. So, yeah, you can now probably understand what is left, at least if I'm not mistaken, this is more or less what is known. What is left is probably a non-closed field of positive characteristic, something like that. Okay. If you know, if you see that I missed something, please tell me, but I think this is pretty much what is known about finite groups essentially acting on Delpezzo surfaces over different fields. Okay. Good. Then let me go to Birational classification of G-Mori fiber spaces. As we understood from the talks of Julia and Susanna, this is essentially the aim of Sarkisov program, to classify Mori fiber spaces up to Birational equivalence. Yeah, so the main theorem, which was mentioned many times, is that any two, the main theorem of Sarkisov program tells you that any two G-birational G-Mori fiber spaces are related by a sequence of G-Sarkisov links. So we need to study the links. G-Sarkisov program. So luckily, in dimension 2, we have the complete classification of links due to Yaskovskych. Well, which is not precise in in some places, but still. So dimension 2. Links due to Yaskovskych. And as you learn, as you learned from the previous talks, well, this. So what is Sarkis? So this, you can imagine kind of a map of different Mori fiber spaces. You go by a link to one Mori fiber space, then you go to some other Mori fiber space. So a priori, you can have like a big and complicated map of Sarkisov links. So many maps to different G Mori fiber spaces. Okay. So maybe it's not like, well, you can study this whole world of possibilities, but there is like an extreme case in a sense when you don't have that many transformations into different Mori fiber spaces. It's convenient to introduce the following definition. Let me definition. I would say that a G-Delpezza surface, here G can be Galois or geometric, doesn't matter. A G-Delpezza surface also you can think about Fano varieties of any dimension. I decided to stay in dimension 2, but everything the same for Fano varieties here. So a G-Delpezza surface is called G solid. Okay, let me put the general definition here. G Fano. G Fano X is called G solid if X is not G birational to any G Mori fiber space over positive dimensional base. So for example, when you work with Delpezza surface, it means that it's not birational to G-conic bundles, okay? And then the definition which is due to Corti probably is the following. Corti. No. Solid is just a word here. So once again, solid. If it's dimension 3, it means that it's not your Fano threefold. It's not birational to a conic bundle over surface or to Delpezza fibration over curve. Threefold, yeah. But for surfaces, it means that it's not birational to conic bundle. Okay, positive dimensional base, curve, fine. So Corti introduced the following definition of G pliability. So assume that X is not that X is G-solid Fana. And basically, he just suggested to count all, so G pliability, he suggested to count all G Fanas which are G birational to X Fana X prime which are G birational to X. Of course, up to G isomorphism. So I count all G Fanas which are not G isomorphic to X, okay? So basically, I just look where I can transform myself to which G Fanas, okay? And there is an important particular case is when this is a singleton, so when it's just one element. So when pliability on G consists of just one element, G itself, X itself, X is called G birationally rigid. So remark, why is this? I mean, this is an interesting property in many respects, but a remark is that if X is G rigid, if X is G rigid, G birationally rigid, and okay, let me put it a bit differently. Suppose that we have that we're in an arithmetic situation. Then what does rigidity of your Fana variety tells you? It means that it's not rational. I cannot go to projective space, right? And this is actually historically how this definition of rigidity appeared. It appeared in the work of Yasinsky and Manin on the classification of, on the Luret problem. So then, the rigidity implies non-rationality. Non-rationality. What Yasinsky and Manin proved, they presented as a counterexample to the Luret problem, is so they proved that the smooth quartic threefold is birationally rigid. Yeah, smooth quartic threefold, yeah, correct. Is birationally rigid. In fact, they even proved that it's birationally super rigid. So there are no birational maps which are non-regular. The group of birational self-maps coincides with the group of automorphisms, okay? And of course, this immediately implies that the threefold is not rational, right? Because the Cremona group is, as we know, is a huge group, right? So yeah, this remark about like kind of the historical concept of context of this definition. What I want to say is that instead of trying to classify, so I give you a finite varieties, finite variety x or Delpech surface x. Of course, you can ask where I can transform myself equivariantly, but it's also nice to focus on a particular case when I cannot go more or less anywhere except x itself, and try to classify G birationally rigid finite varieties. Okay, and this is like a huge topic in birational geometry. Since yeah, I will definitely will not say anything about dimension 3 and higher, so maybe let me stay in dimension 2 and say what is known there. So examples and examples. Of G-rigid Delpech surfaces, I start with example of P2. So G rigidity of P2. There is complete classification theorem due to Sarkovich. He proved that P2 over the complex numbers is G birationally rigid if and only if G is transitive and not isomorphic to A4 or S4. And here transitive means that its lift to GS3 is an irreducible representation. Okay. Lift to GS3. Irreducible. Representation. Geometrically just means that no, I think it's still called transitive. Primitive is the condition on orbits. So transitive, so yeah, geometrically this means what? This means that you have no G fixed points and you have no G, you cannot have like a G invariant line and G fixed point, right? Something like that. So your presentation doesn't split. Okay. So this is a P2 case, degree 9 surface. Degree 8, so Delpech degree 8 is due to me, but I will not give you the list because it's kind of some conditions on groups. Then I think Delpech 6 is open. Okay, Delpech 6 is open. It's a nice problem to think about. And then an interesting phenomenon occurs when you go to lower degrees. The situation becomes rigid. Why? Because, well, as I told you, we have classification of hierarchies of links. Meaning that if I start with Delpech degree 1 or 2, say, then I have very few possible links on the surfaces. As you explained, on Delpech degree 1, I cannot blow up anything, right? Because I need to go to Delpech. There is no way to go. For Delpech of degree 2, I can blow up a G fixed point. Okay? This is already a condition. If there are no g-fixed points in Lopez 2, there is nothing to do, right? If there is a g-fixed point, I can do this kind of a birational Bertini involution. But it's easy to see that in this case, I necessarily contract back to G isomorphic Lopez degree 2, because basically this Sarkisov link is given by the canonical Bertini biregular involution upstairs, which exchanges to extremal rays of my Mori cone, and so you get G isomorphic surface after contraction. So low degrees are rigid. Well, degree 5 and 4 we can discuss if you like after the talk. It's not that difficult. So I think that del beta 6 is the only interesting remaining case here. Good. Good. Maybe the last thing that I want to mention is this question that I like, the one of Janos Koller, which is basically that would be the fourth part, have like 5 minutes, 3 minutes maybe, which basically shows that this property of birational rigidity is quite subtle. The question is the following, maybe from 2006 or 9. Assume that we have now a Fano variety over non-closed field. So, and I know that, so x over k, Fano, and assume that I know that Fano, G Fano, I'm talking about birational rigidity, so Picard log is 1, okay? Such that after I go to the closure of the field, I know that this variety is rigid, birationally rigid. Does this imply that x was rigid over k? Before I explain what is the subtle point here, let me slightly reformulate this question. So this is arithmetic question, geometric question, which is maybe due to Cheltsov. So question prime due to Cheltsov. Now assume that I have a finite group, G, and a subgroup. So H inside of G. Okay. Is it true that H rigidity implies G rigidity? Like, so the question looks a bit weird, but let's just think why it can fail. So, for example, if you look here, why it can fail? Because a priori, it's possible. A priori, it's possible that my Fano x, my H Fano x, admits like transformations to other Fanos, but H equivariant rank of these Fanos is bigger than 1. Okay? But when I take a bigger group, the Picard rank drops, right? So it can happen a priori that I get G Fano, which is not isomorphic to my initial Fano, but which is not H Fano, okay? So a priori this is possible. A priori this is possible. But we have no such examples. And in dimension 2, I proved that, so the answer to this question is yes. Yes. When dimension of, so basically for Delpezza surfaces, dimension 2, and the field is closed, but we don't have any counterexamples in higher dimension, neither in this situation or in a geometric situation, although it's very possible that such examples exist, but it's hard to construct them. Okay. And maybe to add an extra level of confusion, the answer is no when I consider the mixed case, Galois action plus a group. Okay. So I stop here. Thank you.
Questions? Yeah, in the Collar question, in the first one, do you assume something on the Picard rank? Because you assume, it's part of the question that you assume.
Yes, of course. I want to say that the Picard of X is 1, yeah.
Even after passing to the algebraic closure, so it's part of the assumption.
Yes, yeah, implicitly, yeah.
Okay.
More questions?
So you said the answer is no in the mixed case.
Yeah.
What goes wrong?
Thank you very much for this question, because it relates to Fourier surfaces. So here, in fact, okay, what can I erase? Let's say. So the counterexample here is the following. I take. So in fact, the counterexample is ready for h equals g. So when h equals g, so I want to say that g birationally rigid over over k bar does not imply g birationally rigid. Over k. And the trick is the following. You take some prime number p, which is congruent to 1 modulo 3. You consider the group G, which is a semi-direct product of Z mod P with Z3. So here I take some non-trivial homomorphism from Z3 to aught of Z mod P. And then Shramov proved that there exists a field, K, and a Fourier surface non-trivial one over K, so that G acts on this S, and there is an orbit of size 3, okay? There is an orbit with a G point, yeah, of size 3. It's a bit weirdly, so with an orbit of size 3. With an orbit, yeah. With an orbit, yeah. With an orbit. Orbit of size 3. Then, as you beautifully explained, today we have a link at this orbit from S to S op. Okay. G orbit. Link. So this means that S is not birationally rigid, right? Because S op, the opposite surface, is never isomorphic, even without G condition, just not isomorphic to S, okay? Never. But then you go to algebraic closure, where everything becomes just P2, okay? And you use the theorem of Sarkovich. For this group, the projective plane is rigid, G rigid.
Then